In the last section, we talked about decomposing a vector as the sum of two vectors which are orthogonal to each other. Now, if we start out with a non-zero vector in 3D space, there's a plane's worth of vectors which are orthogonal to it. So we want a way to be able to talk about planes, just as we've developed a way to talk about points and vectors. We want a way to talk about planes. Now, one way to specify a plane is like this, to give a vector that's orthogonal to it. But more commonly, we specify a plane by giving vectors that generate it in some sense. So here are some vectors which generate this plane. We say that u and v span this plane. So if u and v are the only directions you're allowed to travel, this plane is all the places that you could get to. For example, the span of the standard unit vectors I and j is the xy plane, because that's everywhere you can get, only traveling in the x and y directions. And these vectors don't have to be orthogonal to each other, although it makes things a bit easier if they are orthogonal. Okay, so now let's say we started with these two vectors, and we want to find a vector orthogonal to this plane. So the cross product of u and v is going to do that for us. It's going to be a vector which is orthogonal to both u and v. So what will it be more specifically? Well, there's an entire line's worth of vectors which are orthogonal to this plane. We want to pick exactly one of them. So for the length of the cross product, that we're going to define to be length of u times length of v times the sine of the angle between them, as opposed to cosine for the dot product. So why do we choose this length? I claim that this is exactly the area of the parallelogram defined by u and v, so the area of this parallelogram. I'll explain why that is in a second. Okay, so once we've specified the length, that doesn't completely pin down what the cross product should be. There's still two options for a vector of that length, which is orthogonal to both u and v. So to choose between them, we use the right-hand rule. If your thumb is u and your index finger is v, then your middle finger will give the direction of u cross v. Or another way of doing this is to say, if you curl your fingers around, curl from u to v, then your thumb will, using your right hand, your thumb will point in the direction of n. And if you used your left hand instead, you would get the opposite choice, the opposite direction for the a vector. Okay, anyway, I'll give you a moment to experiment with this. You can try adjusting the different vectors, and you'll see the cross product as a result. Okay, now let me explain why this expression, length of u times length of v sine of theta, the angle between them, gives the area of the parallelogram defined by these vectors. So if we say this is u and this is v, well, it seems a little bit tricky to, so this is the parallelogram we want to find the area of. Since this is slanted, it's not immediately clear what the area will be. But if we draw like this, we can clip off sort of the excess and then move this guy over here. So the area of the parallelogram will be the same as the area of this rectangle. Well, so one of these lengths, this bottom length, is length of v. Then this vertical height, so if this is the angle theta between them, the hypotenuse is length u, so this will be length u sine theta. And so when we multiply those, the area will be length u, length v, sine theta. As a corollary, we get that if u and v are non-zero, so neither of these are zero, then the cross product of u and v is zero if and only if u and v are parallel, because sine theta will be equal to 0 if and only if theta is 0 degrees or 180 degrees. And in both cases, u and v are parallel. So compare this to if u and v are non-zero, their dot product is equal to 0. Note here, for the dot product, 0 the number. For the cross product, it's 0 the vector. if and only if u and v are orthogonal. That's sort of a complementary property. Of course, we need to discuss the algebraic properties of the cross product. So first, if we scale either of the vectors in a cross product, we can pull the scalars out. Next, cross product distributes over addition. And again, this is what justifies calling it a product, a form of multiplication. Now, where things get interesting is the cross product is not commutative. So v cross u is not the same as u cross v. But it's not just any random other vector. V cross u is negative u cross v. So this property is sometimes called anti-commutativity. It just changes by a sign. And this is because when we're using the right-hand rule to select the direction of the cross product, if you take v and u in the opposite order, you'll get the opposite direction. Then 0 cross anything is 0. Then if we take the cross product of 3 vectors, we get this interesting formula. I'll come back to this one in a second. And finally, the cross product is also not associative. So the formula for this expression will look similar to this one, but they're not the same expression. You could work out the exact formula by combining this rule with rule number 3. Okay, so the dot product behaved a lot like the multiplication that we're used to, but the cross product is a stranger beast. So to prove these, it would help to have an algebraic formula for calculating the cross product. We'll get to that next. For now, try to convince yourself of at least these ones just from the geometric definition. Now, for the interesting one, number 5, so the explanation for this is v cross w is orthogonal, so I'll use the symbol for perpendicular sometimes, to both v and w. And then the cross product of that with u, so this is going to be orthogonal to both u and v cross w. But if it's orthogonal to v cross w, which is defined by being orthogonal to the plane spanned by v and w, then that tells us that the answer is going to be something times v plus something else times w. So being orthogonal to this tells us that it's going to have this form, and then we just need to figure out what the question marks are. And then in order to be orthogonal to u, that's what pins down these coefficients. So if we dot this with u, we dot the right-hand side with u, that'll give us u dot w times u dot v minus u dot v, this is v, dot u dot w. And so it's equal to 0. So that's the explanation for this formula. Okay, so now for the actual formula. So first, I actually have to tell you a new notation. The determinant of a 2x2 array of numbers like this is defined to be AD minus BC. So we multiply along the diagonals and then subtract. And then a 3x3 determinant is, so this looks a lot more complicated, but how it works is we go across the top row. So we start out at A, and we delete the row and column of A, and then we take A times the 2x2 determinant of what's left over. Then we go to B, and we do the same thing in terms of deleting and multiplying, but now we get a negative sign here. So the signs are going to follow the rule like this. Then we go on to C, we delete this, and we take that 2x2 determinant with a positive sign now. Another way to remember these signs is, so if we expanded this out, here we're going to get AEI minus AFH. So that's AEI minus A, and then it wraps around FH. Then this expanded out will be minus BDI, and then plus BFG. So BFG wraps around, and BDI. And then finally, so this will expand it out, be CDH minus CEG. So here we go, CDH, CEG. So the ones that are going down to the right have positive signs, and the ones going down and left have negative signs. So, for example, the determinant 1, 2, negative 1, 1, this will be 1 times 1 minus 1 times 2 is equal to 3. If we took a 3 by 3 matrix, 1, 0, negative 1, 1, 1, 1, 2, 0, 1. So this is going to be 1, 1, 0, 1, minus 1, 1, 2, 0, which is 1 minus 2. So this will also be 3, although that was just an accident. So the reason for this mysterious determinant formula, you can check that if AC and BD are vectors in the plane, then the absolute value of the determinant, so abs ABCD, is the area of this parallelogram. And the sign will be positive or negative depending on, again, the orientation, sort of which, if you go like this or like this, depending on how you've, which order you've put the vectors in. Okay, so now the formula for cross product is we take this determinant with the standard unit vectors I, j, k in the top row and the entries of u and v in the next rows. This is in scare quotes because what does it mean to put a vector inside a determinant? So this is sort of a slang notation for writing out this expression. So the coefficients of I, j, and k are given by these 2 by 2 determinants, but this expression is an easier way to remember that formula. So you probably wouldn't have guessed this formula from the geometric interpretation we've given so far. So the key to this formula is first the multiplication table for the cross products of the standard unit vectors. So the way this table reads is it's row cross column. So this is I cross j, this is j cross I cross j is k, and j cross I is negative k. So you should convince yourself of this table geometrically, maybe using the demo from the start. Okay, so now for a general vector, two general vectors, u cross v, this is u1i plus u2j plus u3k cross v1i plus v2j plus v3k. So now we expand that out using the distributive property for the cross product, and we get u1 v1 I cross I plus u1 v2 I cross j plus u1 v3 I cross k, and then plus u2 v1 j cross I plus u2 v2 j cross j plus u2 v3 j cross k plus, and then finally u3 v1 k cross I plus u3 v2 k cross j plus u3 v3 k cross k. But now, since any one of these crosses with itself to 0, we get a cancellation here. And then in the remaining ones, so I cross j is k, j cross I is negative k. So when we're expanding this using the distributive law, we have to be very careful about the order of these, because that's sort of the whole point here, is the cross product is not commutative. Then I cross k, this is negative j, k cross I, this is j, k cross j, this is negative I, and j cross k, this is I. And so now we look at these coefficients. Well, so u1 v2 minus u2 v1, that's exactly this determinant here, which is the coefficient of k.